puede vivir así.
Bueno, ahora es el turno de Miros. Of course, we are going to change the language to English, okay? So I'm sure that everybody knows him. He's co-creator of the tool SQL Map, among other things, of course. And today he's going to speak about deep learning for detecting malware. So we are going to wait 1 minute, and then we are going to start. One second, Miros.
The way of the warrior is fighting with honor, fighting against the evil, is resolute acceptance of death.
Fuego, agua, viento, montaña, el camino de la espada, la palabra como arma. Fuego, agua, viento, montaña, el camino de la espada, la música y su magia. Fuego, agua, viento, montaña, el camino de la espada, un baile entre las llamas. Fuego, agua, viento, montaña, el camino de la espada, ¿no oyes su llamada? El camino de la espada es un arte milenario, es acero forjado por la sangre y el llanto. Sigo atormentado por recuerdos del pasado, el sueño no es grato, Orovia ha llegado. La música y su magia no calman la tormenta, hay un silencio roto, a punto de llorar, las heridas del cuerpo cuentan mi pasado. Sigo caminando bajo el techo de Susano, un baile entre las llamas, la danza de la espada, un pueblo oprimido necesita de mi auxilio, asesinan niños y no puedo permitirlo, desenvaino la katana y al campo de batalla. Oyes la llamada, un grito de venganza, la justicia de Batman condena a mi monarca, granjeros, las armas, la guerra nos reclama, si no te queda nada, forjemos una hazaña.
Bueno, vamos a empezar, ¿vale? No sé si alguno quiere ir al baño o ha vuelto. Va a empezar Miros. Miros, when you want to start. No problem. Okay, thank you so much. Y otro aplauso, por favor.
Hello, everybody. My name is Miroslav Stampar, and I would like to present the topic using deep learning for detect malware on network. So, just a short slide who I am. So, apart from my obviously famous offensive tool, I like to do the defensive tooling too. So also in real life or as part of my everyday activities, I'm doing the blue teaming. So I like to really detect malware, analyze malware, and do anything related to malware. So I'm currently working as a senior malware analyst at one threat hunting company. I'm CEO of my own small company, and so I'm the contractor of this company from the United States. Recently, I acquired a PhD in computer science, and this topic is excerpt from my thesis. So also, in free time, I'm doing CTFing for one of top-tier teams called Supergasser. So if anyone from my team will watch this, I say hi. So, as the introduction, things that previously in my, I would say, regular research, I did lots of machine learning. So I used my acquired knowledge also in my PhD thesis. And the thing is that as in everybody's life, when you get rejected in any part of your life, then you try to prove that other part or that other guy is wrong. So I started messing with the deep learning basically just because I got rejected because of my usage of machine learning in this topic. So this is I would say, the basics, or I would say, introduction into this whole topic. So you have a huge topic called artificial intelligence. So anything mimicking the human expert or human decision making can be called artificial intelligence. Even some heuristics done in a couple of lines, it can be put into the artificial intelligence department. Then you have the part of artificial intelligence called machine learning. So if you have the algorithm that is trying to learn data that you provide to him, it is automatically called machine learning. Then you have something called deep learning. That's part of machine learning. It's the recent evolution of the machine learning. So it is trying to learn stuff better. And that better can be best described in this line here. Sorry. Is there a pointer? In this line here. So basically, the deep learning is nothing more than the machine learning with more layers inside. So previously, it was a problem to learn all those layers inside the machine learning. So recently, researchers found a way how to make those networks bigger and better and how to learn better. So that last line says deep learning is basically machine learning which is deeper. Then Graphicon. So as said, artificial intelligence is this whole topic which has inside the machine learning, and deep learning is only part of machine learning, which just got into the attention in last 10, 20 years. So if you look into the graphs of how one machine learning network, how can be presented as the network, and the deep learning network, you can see here you have a couple of those layers, while inside deep learning you have more. So this is I would say, the most important thing related to the machine learning. So you have a feature. So to properly do the learning of that machine learning algorithm, you have to find all those characteristics of that data that you want to process, so the machine learning algorithm could learn from it. So features could be length, weight, color, anything related to the data that you want to learn the algorithm itself. Then you put or extract all those features and put into the vectors, and you provide to the machine learning algorithm. So all those vectors are called feature vectors, and these, if you ever stumbled upon some research papers, if you've seen things like these are machine learning algorithms. Deep learning is the evolution of the machine learning. So deep learning does not require features. So this was kind of a new thing to me. So I was not doing the deep learning stuff. 2 years ago, I didn't honestly know anything about the deep learning. So my paper got rejected because I used the old stuff called machine learning. While recently, so in last year, I was deeply involved into the deep learning, and one of the first things that you learn is that deep learning does not require features. So that's really cool thing, especially because you don't have to be an expert in the field. You just have to provide a proper set of data to that deep learning algorithm. So these are, I would say, famous deep learning networks. So if you've seen some of those, you can know now that those are related to the deep learning field. Particularly the CNN, LSTM are, I would say, the most famous. So how does it look like from the researcher's point of view? So machine learning, as said, you have to have a proper set of features which need to process the input data. So that's called feature extraction. So the machine learning algorithm could deduce something from this same data. In deep learning, you just have to properly describe data in some numerical form. Usually that's some n-dimensional vector. In this case, it's an image, so you just have to provide it 2D data to the deep learning algorithm. It will try to learn from it, and at the end, you will get the result. So this same thing is missing here, and that's a cool thing. So now I will show you 2 examples where I used machine learning and the deep learning in my own research, where I've spotted or where I have seen that deep learning is really, I would say, a powerful tool. So first one is the deep generation algorithms. You have malware that at everyday basis generate lots of domain names. And cool thing about it from the malware point of view is that you can generate thousands of domain names per day, and the author or the operator at the other side has to register only one domain to successfully communicate with the malware. So what's a problem from the defender's point of view? This is a problem. So to gather all that data, store and distribute all those blacklists containing all those domain names is really a problem. So nowadays, the appliances do not use it because it will require lots of resources, lots of downloading, lots of memory and stuff. So currently, there are 50 or 60 major malware families that abuse this kind of algorithms. And on a daily basis, the whole list of those domain names generated by those malware families can go up to 500 megabytes per day. So that's a really problem to distribute, gather, and store for the defenders. So from the network analyst point of view, when you are analyzing the data on your network, you can spot these kind of, it's called clusters. So you have IPs communicating toward domain names which are obviously not human-made. So something fishy is going on here. So here you have a cluster from one IP that is communicating with the config at DGA. So on a daily basis, there are around 100 domain names generated or by that same IP address. So from the network analyst point of view, we are trying to automatically detect this kind of network behavior. When you use the Wireshark in this case, on your network traffic, you can see this kind of, I would say, anomaly inside your network. So here you can see that the queries were not successful, and the result was no such domain name exists for obviously algorithmically generated domain names. So from the human point of view, it's really easy to spot this kind of behavior. Problem is how to learn the algorithm to detect this. So how to detect it? First thing is that you try to collect all those no such name domain names from DNS traffic. So you will get a huge, especially if you are working with the huge pipes, you'll get lots and lots of invalid domain names. Then you try to extract their main names. So in this case, there is KFO, this, and this. So extract this kind of main names, and you try to calculate the feature values and provide to the machine learning algorithm. And in case of deep learning, you calculate value vectors. I'll show you how. So in case of machine learning, so I spent, I would say, lots of time to properly find these features to properly extract the feature vector from all those domain names. So this was a really tough job. I spent a couple of weeks. Also, lots of researchers are just focusing how to really find something that is usable by the machine learning to get proper results at the end. So here you can see stuff that is easy to conceive, like the length, entropy, digit ratio, but these things at the end are, I would say, the most important. So here, if you see a number which is higher than usual, so up the number, the less human the domain name is. So in this case, those 4 grams, or I would say those pairs of 4 characters inside the domain name, if they are not, I would say, usual, this same number will go up. And this kind of, I would say, human deduction is automatically being conceived by the machine learning algorithms. So how does it look like from the code point of view? So this is the simplified version of one machine learning algorithm. So in this case, I use random forests. I use the function called calculate vector, and all those features I showed you before are just appended into one vector and just being pushed, you can see here, to the model, so it could learn from it. This fit function is actually the learning point of the machine learning algorithm. So here, inside the X, you put all those vectors, feature vectors calculated by the provided domain names. So you can see here all those values for the example com are just being put into this vector and provided as part of the X. And inside of epsilon, you put the final value. So value that you know that is either false or true. So in this case, we want to mark this example as non-DGA. So we put false or 0. In case of the DGA, we will put here 1. So we provide these vectors X and Y to the model fit, and machine learning algorithm will automatically learn from it. And later on, you have to try to find out, okay, whether the next domain name we put inside, whether it is the DGA or not. In case of the deep learning, we have slightly different situation. So we have the reduced ASCII table with all those valid symbols. So you can see valid symbols on the right, and here are the values which are being substituted from those original characters. And the thing is that in deep learning, you just have to, in this case, you just have to do the substitution from the original character to this numerical value. And if you put it into the vector form, you'll get this kind of vector, which are nothing more than the, I would say, reduced ASCII indices. And how to put it, or how to learn the deep learning algorithm based on that data. So, thing is that deep learning, this may be the main point of this whole presentation. Deep learning is really not a boogeyman. So this really are copy-pasted stuff. This is all copy-pasted stuff for one standard deep learning network. So in this case is the CNN network, which has this same lane inside. And if you just copy-paste this and provide this same model with your X's and Y's, and if you try to learn the data provided by you, you'll get, I would say, your first deep learning experience. So at first, when I started, I really thought that this will be tougher, but at the end, I read hundreds of deep learning papers, and it all comes to this. There are standard set of models. They are used at a standard way. Usually it is Python keras, so you just append to this model different layers, which are predefined. You just have to take care of proper x and y's. And the data that are provided to this same model is this. So at the left side, these are the domain names from the Alexa, 1 million, so list of top human domain names. At the right side are the DJ domain names I collected from different sources. So basically, you have to just use these, fill into this same method. So you just substitute all those characters with their substitutes and fill the deep learning model. And now, so you don't have to read everything. I'll just shorten it for you. Greens are the machine learning results. Blues are the deep learning, and that red one is the heuristics. So that was for the comparison. At the end of the day, so when I first saw this, when I got these results, I was quite happy because I proved that machine learning, if properly being set by proper set of features, you'll really get better results than the deep learning. That's a fact. And that fact you won't see in research paper because, as seen in the introduction, I haven't remarked it. Thing is that currently there is a huge bias toward deep learning algorithms. That's my honest opinion. But thing is that I started eventually to like them because the difference in the overall score is marginal. So if you go to this last column here, you will see that these results, so 0.95, and you will also see in deep learning 0.95. So results are really marginal, but the good thing is that you don't have to do the feature engineering. So I spent a lot of time to find those proper set of features, and that same task is really hard, especially if you're not the expert in the field. So there's one anecdote. So I got rejected by this machine learning when I didn't mess with the deep learning stuff because one authority in the field, she said that deep learning is better than the machine learning based on her own experience. And I was really trying my hard to find out what's going on. Why do I have better results for the machine learning? And she has dramatically better results for the deep learning. And the thing is that I've seen her set of features was wrong. And when I say wrong, I really contacted her and said, okay, are you aware that you use one feature which is obviously wrong, which reduces the performance of the machine learning? And she said, okay, my fault. I am aware of it. And the thing is that she used, instead of the proper set of domain names, she used English vocabulary. And the thing is that currently, when you think about all those domain names currently being used all over the internet, first thing that comes to your mind is it is English, but that's not the general rule. So in 60% of cases, you will have really some English word inside, but in 30 to 40% of cases, there won't be any English inside. So she used, I would say, wrong set of features. But I proved with my own research that if you use a proper set of features, you will get better results with the machine learning. But, as said, deep learning does not require this feature engineering. You don't have to be an expert in the field, so you don't have to know really what to search inside the data. You just have to properly put the data into the proper format and put into this something like this. So honestly, if I would go back in time, I would just copy-paste this and fill it with data and try it. Now the second thing I wanted to show you how I used deep learning in my research is the periodic CNC beaconing. So all malware wants to contact its CNC to get proper set of commands from the other end, updates to exfiltrate data from your own network. So usually it does this kind of stuff in periodic manner. So it will try to contact, for example, its CNC, in this case, every 5 seconds or every 5 minutes. You'll have these red lines. And you can see here with blue, you have this noise. So you have to, if you have a huge pipe with lots of traffic, you have to somehow find all these red lines. And it seems that deep learning is really good at this kind of stuff. So to show you why. So deep learning is really good at finding patterns. So if you provide any kind of, I would say, image-alike data, so two-dimensional vector, like in this case, and if you, as a human, can see, okay, these reds are really different than these blues, you can be sure that deep learning will do that too. Because deep learning really tries to find these kind of spikes inside the data, everything that is different from normal. So you say, okay, this is normal, this is not normal. Deep learning will try to do the deduction as you, as a human. So here you have the flat line around all those even time differences. But in case of malware, you have majority of those CNC beaconing will go around some time. So in this case, the period was around 400 seconds. In that kind, the beaconing was around the 900 seconds. So all those beacons just piled up. Another case, so here you also see those spikes in case of malware, and in case of regular user contacts, you can see nearly a flat line. How does it look like when you collect that data on the user's traffic? So this is really collected from the user's traffic. For example, in this case, you can see pattern, right? So you can see that something is going on around the 1600, something is going on around the 4700. Here you can see that something is going on around the 180, around 76. So as said, if you put all those differences into this kind of graph, it counts on the y, and all those attempts at the x, you'll see spikes like this. And thing is that up until now, this same phenomenon was extensively researched, but when you try to use all those existing, I would say, mathematical algorithms, they are not practical in real life. So in this case, the deep learning was really, I would say, useful, because the malware does that distinct visual behavior, which deep learning likes to learn inside the provided data. Also, the thing is that this all started with our initial impression that malware really behaves significantly different, or I would say in periodic manner. So this was the premise of this whole research, and at the end, when we started to really collect this kind of data, we noticed those spikes. And if you feed all those spikes, so if you feed all this data to the deep learning, and if you properly, I would say, pre-process, so in this case, all those spikes like this, they were sorted in this form. And there is a reason why. So instead of providing this kind of data, that sorted form was really good because you could reduce any number of events to some reduced form. So in this case, maybe number of events was thousands, but we only, I would say, sorted out to those most occurring toward the least and just took the first and events or periods. And we provided this kind of image data to those deep learning models. And at the end, we got these results. So by feeding to any of deep learning algorithms, you'll get really good results. So that last column is actually the result of this whole research. In this case, this same SRNN, we got lucky, to be honest, because when I tried to remodel the data, I got slightly different results, or I would say the order of these models. But at the end, everything was, I would say, everything was around the 0.9899. And that's basically it. Just to conclude, so I started this whole research as, I would say, my fight to prove that machine learning is better, but at the end, I would say, ended in liking the deep learning. It is indeed the evolution of machine learning, and this second line is the important one, where I learned that this same automatic extraction, so removal of that feature engineering, or removal of this whole human expert, is really, I would say, the ease of the new researchers in this field. Also, if you can transform your data into any kind of n-dimensional vectors, most probably the deep learning will be able to learn from it and will be most probably successful, maybe more successful machine learning in some cases. It is easier to use than you might think of. When I started, I really was under the impression that deep learning is something boogie. But at the end, I've shown you there is an excerpt. You just have to copy, paste, and provide with proper set of data. And this is the general case. So you will use Python, Keras, and the TensorFlow to set up your model. This same, I would say, general case was shown on that slide. You'll copy-paste between different projects. You just have to take care of the data. And that's it.
Thank you so much, Miros. Any question for Miros, please? No questions? It's okay. So I think you are speaking very, very clear.
Okay, thank you.
It's a pleasure for us, Miros, to hear. So thank you so much.
Thank you.
And let's go with the Miros question for all the people. Let's go. Remember that we use menti.com. Please, the question? Thank you. featureless processing characteristic of. And you have 4 answers. Three, 2, 1. Let's go. Oh. Yeah.
Nice.
Yeah. It's not a surprise. And the winner is Tom. Please come here. Tom, please. Who is Tom? So we have a present for you. Tom, ¿andas por aquí? Si no estás por aquí, no, pues vamos al siguiente. ¿Quién ha sido el siguiente? Joana. Aquí tenemos a Joana. Muchas gracias. Gracias, Joana. So, he is Joana. So, in Spain, it's a name of a girl. Thank you so much. Come here. So, the present, it's here. It's a beer. Thank you, too.